Welcome everybody to this week's feature, Lessons from North America's Tightest Building Enclosures, featuring Graham Finch from RDH Building Science. My name is Peter Barrett. I'm the Product and Marketing Manager for Dorken Systems North America. Dorken has been in the construction materials business for 125 years. This is a lovely shot of our head office in Herdecke, Germany. You can see that it's been there for quite a while. That's where all of our membranes originate. Our plant in North America is located in Beamsville, Ontario, which is about an hour west of Toronto. Our presenter today is Graham Finch. Dr. Joe Stebrick has called him the brightest mind in building science today. He is a principal engineer and building scientist with RDH Building Science based in Victoria, British Columbia. Graham specializes in enclosure design, research, investigative work for new and existing buildings. He works with building product manufacturers such as ourselves and other clients on product research and development, performance monitoring, forensic investigations, and field testing. His recent work has been focused on the high-performance building enclosures and guidance on improved air barrier systems in achieving airtight buildings. That recent work is a good chunk of what he is going to share with us today. Without further ado, I present Graham Finch. Graham, welcome.
Hi, Peter. Thank you for having me here today. We have a lot of designers here today. A lot of the presentations can be focused on airtight building designs, and it's great to also have contractors and vendors and installers here because we're going to get into the detailing as well. All right, thanks everyone for attending. Today, I'm going to talk about lessons that we've learned from North America's tightest building enclosures and share a lot of new data that we've been putting together and also some anecdotes that we've been seeing that have resulted in very airtight buildings, and often quite simply. We're quite surprised by a lot of the tight buildings we're seeing nowadays up in the Pacific Northwest here, where we're doing a lot of testing. And I want to share those lessons here with everyone. So just disclaimer here. All right, so today I'm going to focus on three things. And those three aspects of the presentation focus around the three keys to airtight buildings. And those are starting with design. And design includes your material, your assembly selection, your detailing, creation of buildable details, and you're designing potentially for a target to exceed that target. The second is build. Okay? Build includes the construction, implementation, compatibility, materials, workmanship, mock-ups, and other things which we'll cover today. And the third is confirm. Okay? And confirming includes the visual review, your QA/QC, your qualitative, and your quantitative tests. And we'll talk about how these three things, the design, the build, and the confirm, the whole process, and you repeat and repeat over and over again on projects, will achieve you airtight buildings. It's something we consistently see, and we've been able to just distill this down to three key aspects. And it's important to realize too that all three must be present. You need all three of those. If you neglect one of them, then bad things happen. And as enclosure engineers, we see lots of fun, but also bad things. And we'll share a few of those as well here. So this is a project we worked on a number of years ago. We got called in to do airtightness testing at the end of construction. And really, this was an example. This is as the building's been turned over, we're doing smoke testing and the building's leaking air everywhere. Really an air barrier system that's not continuous. And this is an example of confirming too late. The confirmation was done at the end. It could have been done earlier on to avoid this. The design and the building, appeared adequate, although some issues resulted. And this is a result of confirming too late. A lot of air leakage, something you don't want to see on the last day before you turn the building over. We see lots of examples of this where a builder will build something and then they'll confirm it and only to find it doesn't work without doing the proper design. We've been involved with many passive house projects here in Canada and the US. And on some of the earlier projects, we found that the builders are struggling to achieve airtightness targets, so they would try band-aids and different approaches. On this particular project, the builder spent about $20,000 in spray foam to try to fix. They were coming in at 0.7 ACH to try to fix some air leakage, only to spend all that money and not impact the airtightness at all. It was basically the insulation was put in the wrong spot. It didn't actually address any of the holes in the air barrier that were there, and a lot of money wasted. So this is an example of a builder going down the wrong route without really looking at the design. So we see this as well. So if you don't get the design right, or if you just charge ahead and don't consider how the air barrier is designed, then you can run into problems too, and confirming results later on. We see a lot of this as well, as arguably unfinished, but to achieve air tightness with this mixed approach here is going to be very challenging. The designer might have said, you'd house wrap as an air barrier. The confirmation here is quite obvious in the visual review, and there's going to be a lot of challenges to make this airtight. And so when you find projects like this, you really got to look back at the construction and the builder here and saying, okay, what happened and what missed? So let's fix this. And then we also get involved with a lot of forensic investigations where arguably there was poor design or an air barrier system that wasn't well designed or detailed. It wasn't implemented in the field, and there was no confirmation. The confirmation here is 10 years later, when air leakage condensation rots out half your building here. So it's very important to obviously do all three of these things. And we've got many examples. I'm sure many people on the webinar here have examples of cases like this where one of these was missed. So air tightness matters for a number of reasons. Airtight. We talk about air tightness, and the reason we want airtight building enclosures is to control air leakage. The air leakage, the infiltration and air exfiltration from air leakage directly impacts your energy consumption, so the dollars and the money in your pocket at the end of the day. The indoor air quality, outdoor air pollutants, but also control of indoor air as well is more difficult with air leaky buildings. Building durability, lots of examples of condensation, moisture, mold, and decay that gets into spaces it shouldn't, and air tightness is directly related to this. And then occupant comfort. And more these days, people are demanding higher levels of comfort, both thermally, but also acoustically as well, and air tightness plays a big role in that. Air tightness matters everywhere. People typically think of air tightness as a cold climate problem, but it's just as important in hot, humid climates and hot, dry climates and all across North America as it is in the north. And so it's very important to realize that this is not climate specific. Air tightness matters everywhere. So we're going to talk today a lot about details and ways to improve design and practices and implementation. How do we know this? Well, we do a lot of investigations. We do a lot of testing. We're fortunate to be in markets that do a lot of testing or requiring a lot of testing. And so we're here to share that with the rest of the countries here. So, and seeing things. We also have a lot of tools, infrared cameras, smoke, other diagnostics that help you see air leakage. If we all had X-ray vision, we'd be a lot better at this. But there are tools at your disposal that can be easily used to identify air leakage. It's not that hard. We also collect a lot of data. Because we're testing a lot of buildings, we're taking all that data, putting it into databases. We're taking other people's databases and comparing the data. And I'm going to share a lot of data here today to show what's happening and show what's working and what's not. So in that database that I'm going to be sharing today, it's a large building database. It consists of commercial, multifamily, and institutional, roughly a third of each of those building types. There are buildings across North America. We've got, in the whole database, there's 754 from various sources. The data that I'm going to be parsing out and looking at specifically today, because I can talk to them directly, are buildings that we tested. There's about 209 that we've tested, large buildings, both Washington State, BC, and otherwise. I'm going to be focusing in on the Washington State and BC data. It's quite a bit here. We've been presenting this over the last few years since we've been collecting a lot of this, and the database is really growing. We're testing buildings like a lot of people every weekend, every week. So a lot of it keeps growing, and we're collecting that and then trying to disseminate that back here. The other unique thing about this database is it consists really of a mix of research and code minimum, and also passive house projects. And passive house and net zero projects are unique in that they're going for a very high level of airtightness. Code minimum projects, you get varying performance there. And the research projects are interesting because they're often on buildings that didn't have a target. And so we've learned a lot from that as well. So the first of our three keys is design. Okay, so we're going to focus a lot attention here on design and how designers, for a large part of the group here today, can put together good air barrier designs and details that will lead to success in the field. Okay, the first thing to always remember with air barriers is they're not one material, they're always systems, and these systems consist of many materials: house wraps and peel and stick and roofing membranes and tapes and below grade membranes and concrete, wood. Every building material that you're using can all be part of that air barrier system. We got accessories that go with these materials, caulking and sealants and tapes and peel and stick, and then components like windows and skylights and doors. And all these are put together into our building enclosure assemblies to create whole building airtightness. Air barrier systems, as a result, are unfortunately only as strong as your weakest detail. And the challenge on big buildings is you have many trades, many different systems coming together. Office building, represented here, you've got curtain wall systems, you got ribbon window, punch windows, and below and above grade, you got roofing and parapet details, which we'll talk about today. And the overall performance of this building is going to be dictated on the worst location. And so it's important to identify those and figure those weak spots so you don't run into those problems. And if you address those weak spots, then we often end up with very airtight buildings. When we look at requirements and standards in the industry, we have three things we look at. The first is materials, and materials themselves for air barrier systems have to meet a certain air permeability. It's not that difficult, to meet this requirement for most materials that we use for air barrier systems. And also the air tightness of material doesn't directly necessarily result in a more airtight building. It just means we have to use these materials. We've done silly tests and things, on Friday afternoons where we've tested the air permeability of peanut butter and found that peanut butter, for example, would easily, exceed this target if you just slathered it onto some plywood. But, it's really not, it's more than the material. The other thing that you're going to be looking at for materials, so that's a code requirement, then assemblies are also looked at in code. And air barrier systems and our assemblies, they have an air leakage target of no higher than 0.2 or 0.04 if you'd like the imperial units. And you can see that's 10 times higher than the material. And if you look at buildings, and there's many standards now for buildings, E779 and 3158, which is a new standard, and US ACE and others, they're used by Passive House. Generally the target in these standards, although they don't often include a target, is less than 2 liters per second or 0.4 CFM 75. And so you've got materials and assemblies and buildings, and those are the three things you're looking at. What's most important at the end of the day is how your building's performing, but the materials and assemblies you use have to be airtight, of course, as well. When you look at targets, across North America, we have different targets now, depending on where you are. Some states, building types, code requirements in different states and provinces have pushed air tightness requirements for whole buildings. And you see a range of numbers, like it's just looking at the imperial numbers here, 0.3 to 0.4 CFM at 75 square feet. These jurisdictions, US Army Corps, 0.25. Passive House talks about 0.6 ACH when you convert it for larger buildings. It works out roughly, depends on the surface to volume ratio, around 0.12. And then FIAS, the new standard, 0.08. So you see this sort of range of 0.08 to 0.4, something that's, 5, FIAS you could say is 5 times tighter than the minimum here. So, looking at our database here, one of the first things we see consistently is the impact of test requirements on airtightness. Just having a requirement will typically make your building more airtight. And I'll show you in a minute here. So we've got data here. We've got 29 buildings that were tested, let's say for fun or for research, more or less, modern construction in the last 20 years. On average, modern buildings, 0.3 CFM per square foot at 75. a range of 0.12 to 0.48 or so in your quartile there, and a minimum maximum. So quite a range, quite tight to quite leaky. Just being built without a test requirement. So when we look at our buildings being built for test requirements, and we've got three cases here, three groupings of projects. We've got USACE, so U.S. Army Corps of Engineers, target of 0.25, and this is data from the U.S. Army Corps here. You can see on average, you can see they're around 0.2, and they're exceeding the target on average. There's a range, of course. Buildings are tighter and some are leakier. Washington State, the target for many years is 0.4. It's now down to 0.3. But looking at the buildings that were 0.4 was a target, you can see that on average we're getting around 0.25. And in British Columbia, where passive house, it's not a requirement for all buildings in BC, but many buildings are going for passive house. And so you can see here the target for these projects is 0.12. And they're actually blowing that away and getting some are on average much tighter than passive house. So this is a very high target already, and we're killing it there. The other thing to look at, and specifically of Washington versus BC in this case here, in Washington State, if looking at Washington versus BC, so BC for step code projects, the target is 0.4, which works as 2 liters, which works out to 0.4. And in Washington for many years was 0.4 as well. In BC and in Washington over those years, there's been different, let's say, enforcement of that code, but that target, but that's essentially been what people have been aiming for. And you can see in Washington, in BC in particular, you can see that, on average, buildings are coming in quite a bit tighter. When in Washington moving to 0.3, you can see the buildings are getting tighter still. It's also newer buildings as well. When you look at a couple of FIAS projects here, there's many more FIAS projects across the US, you can see that they're coming in twice as tight. And then many passive house projects here as well in BC, a whole bunch of them, and coming in much tighter than they needed to be as well. So just having that target, if you have a target like PHI or FIAS, then you're likely to hit that, and actually have to hit that if you want to get passive house certification. The other thing to notice is that very few buildings are failing. If you look at a couple hundred buildings here, there's only a handful of buildings that have actually tested above 0.4. It's not to say it's easy, it's a walk in the park, but it's important to realize, these are buildings that have been tested with a target. If you tested a whole handful of buildings, 200 buildings without targets, you probably have quite a few here. So people are aiming for here and generally hitting them. And we have a lot of very airtight buildings, and I'm going to talk a bit about more of them today. The target for passive house is 0.6, and many and quite consistently we're seeing passive house projects come in the 0.2 to 0.3 range, so twice as tight as they need to be. Several up around the 0.6, but quite a few. And I'll talk about what makes these really tight projects really tight later on, and it is really that design, build, confirm process with the right materials and the right details. So I'm going to talk here now about air barrier systems and what goes into air barrier systems. When you look at air barrier systems, there's 5 criteria, and sort of represented here. We've got air impermeable materials, continuity or continuous around the entire building enclosure, below grade, above grade, roof, wall, windows, everything. Durability. It used to be durable during construction, but also in service if you want it to last. And then you can really group together strong and stiff, and we've also added and supported in terms of the materials you use. They're going to see pressure and they're going to see load, so they need to be strong enough for the loads that you would see on these projects. When you look at continuity detailing, it's everything. And details occur at every change in material, so your interfaces and your joints, every change in plane, every change in trade. Okay, and this really identifies and highlights some of the challenges we run into, the by others comment that we see a lot on drawings, and the by others needs to be by someone. There can't be by others, and so we're seeing less and less by others comments on drawings nowadays, but it's still a thing that happens. The other important thing to be aware of is, especially as we get into testing larger and larger buildings, can be pretty significant loads on the air barriers of larger buildings compared to houses, where a lot of this, the testing and stuff has sort of evolved from. You got stack effect, which is quite a bit higher on large buildings. You've got wind, which is your biggest load. And then you got mechanical system pressures, and these three acting together create pressures across your building enclosure. And so that, a taller building, larger buildings, especially, taller buildings in extreme climates are going to see higher pressures. And so that wind load in particular gets applied across the air barrier, so it needs to, not be torn off. And I really love visuals, and what really I think helps people understand these loads. I mean, if you're doing air tightness testing, you've seen how temporary membranes and things can react. This is a picture showing this is up in northern Canada and in Yellowknife. I like this picture. I took it there when it was a couple of years ago. It's showing the stack effect loads on this scaffold net, or the scaffolding plastic there. And you can see that the mass amount of pressure in the top and then the suction on the bottom, and really showing that stack effect. And so you can imagine that, okay, this is on scaffolding, it's not really the air barrier, but it is the air barrier for construction here. If you are relying on a loose membrane like this in a building like that, that's what's going to happen inside of the wall if you're not restraining it and supporting it. And so today we'll talk about, how we address that with loose membranes, so we can avoid that. And the stack effect pressures are, 10, 20 pascals, not, hundreds of, maybe even 1,000 pascals like you see with wind. So what makes, an airtight air barrier system? There's lots of choices. There's lots of different materials you can use nowadays. There's really endless choices that you could in particular look at for using in wall systems. You got spray foam, you got drywall, you've got polyethylene and other vapor retarder membranes that can be made airtight. You've got sheathing materials that you can use in wall systems on the inside or the outside. You can seal your rigid insulation if it's air impermeable to be the air barrier. You can use house wraps, mechanically attached house wraps. You can use self-adhered membranes. You can seal the joints in your sheathing. You can ICFs, and concrete, and curtain wall, and a whole bunch of other liquid applied membranes. There's just endless choices. And so, narrowing that down to what's suitable for your project, is one of the first things you're going to look at. So a lot of our commercial buildings are framed walls, right? So they're wood frame or steel stud frame, or potentially areas with concrete as well. And so we're seeing trends, and the four trends we're seeing here. So our top trending, you could say, framed wall air barrier approaches are as follows. We've got loose air barrier systems. We got mechanically attached house wraps. Okay, so there's a lot of products in the market that can use for this. And for rigid air barriers, we're seeing three approaches. The first is sealed sheathing. So the sheathing, the gypsum or the wood, will be taped or caulked with some sort of proprietary or generic sealant or tape, or just peel and stick. It may or may not be overlaid with the water-resistant barrier. It may also be the water-resistant barrier itself. Self-adhered membranes, so many different peel and sticks, and then fluid and liquid applied membrane systems. And the key there is your joints. So these are our rigid air barrier systems and our loose air barrier systems. But we're also seeing a lot of mechanically attached sheet membranes now being sandwiched by the exterior insulation, whatever type. And that sandwiching of that membrane makes that a rigid air barrier, essentially. And we're seeing some really interesting results actually with sandwich mechanically attached sheets, which I'll share you in a minute here. So when we look at air barrier systems, and we're looking at walls here, and so this is looking at the air tightness of whole buildings and grouped by average air tightness based on wall air barrier systems. Now, of course, we have roofs, we have below grade, we have windows and other components. And so everything's coming together. Often a lot of the leakage will be at the roof to wall interface or the low grade to above grade interface. We're not seeing a lot of leakage through windows anymore. Just the way they're sealed up now, it's not resulting in a lot of leakage there. And so you can categorize a bit like this. It's not perfect, but it does give you some sense of what's happening. You know, if you look at Washington and BC projects, we'll talk about some bias here in the data set, but you can see here, you know, mechanically attached sheets, you know, on average, you know, 0.3. In BC, they're around 0.1. I'll talk about why these ones are so tight. Fluid applied systems. Interesting thing about Canada and the US, we see a lot of fluid applied in the US. We don't see a lot of fluid applied in British Columbia at the moment. We see more self-adhered membranes. It's just a matter of the buildings we've tested. There are systems there, it's just not as common, or they haven't been tested necessarily, let's say. Glazed systems, so curtain wall and window wall. Sealed sheathing, so our rigid sealed sheathing approaches, whether you're using tapes or sealants as a group together. You can see a lot of buildings in BC are quite tight with that approach as well. And then our self-adhered membranes, and you can see them typically coming out the most airtight. And there's good reason for that, just the details, and that becomes that rigid air barrier system with this approach. The other thing that's interesting to look at is, you know, in BC, there's a bit of bias just because we have a large proportion of passive house projects coming into this database. So I've separated this last data here for BC specifically, whether the project was going for step code target, and they don't have to actually hit this target here. It's just that's what's put into the energy model, and if they exceed it, then they have to put the higher number in. But generally, people are aiming for this. It's not that high of a threshold. And then passive house projects are sort of down here, and you can see here mechanically attached sheet projects, I should say, are coming in here. Self-adhered membrane and sealed sheathing. And it's interesting, we're seeing a lot of mechanically attached sheet products or projects, you know, coming in quite tight. And we're like, well, what's going on here? And we looked at these. 6 of those 7 projects are sandwiched house wrap. So they're sandwiched house wrap, and I'll talk a bit about them later on. And it's the same modular manufacturer they've figured out how to do very airtight buildings, and they're achieving very high degree of airtightness, pretty much, you know, almost passive house levels on non-passive house projects. You know, self-adhered membrane projects coming in quite tight, and there are no projects that have gone for self-adhered or sort of sealed sheathing that are going for step code. So it's just interesting to see what people are choosing. These are the 3 approaches that we're consistently seeing. We're not seeing the other approaches, or haven't tested them yet. So how do we achieve really tight levels of airtightness with mechanically attached house wrap? Well, it's simple. You sandwich it, and you have really good details in behind, right? So sandwiching it makes it airtight, or sorry, rigid, I should say. It really helps prevent, you know, details from opening up when they're pressurized or depressurized. And in this particular case, we've got a builder who has experience in passive house projects, and they're, you know, using the same details and everything they've learned over and over again for step code or code minimum projects. And so what's interesting is, so, you know, the teams and the experience there with this builder are carrying through on over and over again. And, you know, and arguably they're at a point now where they really don't even need to test anymore, because they're becoming so good at this. When we look at our sealed sheathing system, when you look at sealed sheathing, there's many different proprietary, even generic, you know, you can do it yourself with a good tape and sheathing here on the inside or the outside. You know, lots of products in the market, you know, gypsum based with sealants, or tapes, or wood based, you know, with the WRB, or just plywood or OSB. These systems are working quite well, but, you know, they're 100% reliant on your joints. It's not so much the board, but it's really the joints in many of these cases to get to that high level of airtightness. And so picking the right tape and, you know, the applicator is going to be essential to that. Self-adhered membranes need to stick. It's a pretty obvious one, but, you know, where we see problems is where they're not sticking, and they're usually not sticking because the builder is not following instructions for primers. Always love seeing peel and stick fall off buildings, or the lap treatments. You know, in particular cases, a lot of materials they don't stick that well themselves. So some manufacturers have put in extra adhesive, or they require tape or sealant. When you look at, you know, bituminous sealant, you know, bituminous peel and stick to get that to high levels of airtightness, they're often caulking the joints. You know, you see every slap will be sealed up just as extra measure to make sure that you know, if they peel off or they're not well bonded, then they're remaining quite airtight. Fluid applied systems, where we're seeing them, are all about all about preparation of your substrate. It's a lot like paint, right? Where you have to, in painting drywall, where you have to seal your joints with a joint treatment, and whether that's a mesh or tape or caulking, that is critical. And if the tape doesn't stick that well, or things get wet during construction, this is all really falling back onto the applicator and the contractor here to make sure that that's implemented. But we see a lot of very airtight buildings with this. And unfortunately, when things go bad, we can patch these up, but it takes that confirming, and it takes that inspection to make sure that they're airtight. So with fluid applied systems, when you're shifting to field labor, you really need to be on top of your confirmation. So looking at those systems and looking at detailing here, we're going to share a few lessons that we've learned about detailing, and in particular roof-to-wall interfaces, as we're talking a lot about walls today. So a number of years ago, when we were looking at a study for the Canadian government, we were looking at where buildings were leaking the most, and we polled people doing airtightness testing, infrared scanning, to tell us where they were seeing the biggest problems. So looking across the industry, and you can see here roof-to-wall transitions, pretty high. Mechanical penetrations and dampers are quite high and consistently be high. And then you got soffits and vented roof and base of wall. Things like windows and center wall, of course, is not showing up there. And so when we look at these, a lot of these have to do with roof-to-wall interface areas. And so we've been paying a lot of attention to that area of the building and how we can improve the airtightness. So I'm going to do through a little case study, a little thought process for parapets here. So, airtight parapets. So if you're doing an interior air barrier approach, you got insulation in your ceiling, whether it be vented or unvented. If you got an interior air barrier and you're using, say, polyethylene or some other sheet on the inside, roof-to-wall interface, air barrier achieved through here, and actually fairly straightforward, fairly simple, and fairly common. If you got an interior air barrier and you're going to an exterior air barrier on the wall, you need to transition the air barrier through the top plate. It doesn't mean a membrane through the top plate, but lots of different ways that you could do this. You can use sealant, you can use peel and stick, you can sealant in the wood, you can use peel and stick, and you can use tape. There's lots of different, even pre-stripping and house wrap or sheet product in between the plates or top plate, but it's some transition across the top. And this is where we see a lot of failures, I guess you could say, of the roof-to-wall transition for interior to exterior air barrier approaches. Looking at some infrared images here, you can see this is before the drywall's on. So when the drywall does get put on, it does compress the acoustic seal down a bit, but usually we still see leakage that shows up there. Around, it looks tight, but then when you look at it, actually there's small defects or it hasn't been well sealed. These hurricane ties, here, it's just, it's trickier detailing if things aren't, put in the right spot there. Transferring through here can be a challenge. And, using better materials and tapes doesn't necessarily guarantee higher performance. It makes it easier often, but doesn't necessarily guarantee it. Here you can see some challenges they had at the top of the wall here, getting that airtight. If we have, say, conventional roof, and so in the case here, we've got, an air barrier on the roof, and then we've got an air barrier on the inside here. Pretty common approach to make that transition from the roof deck, and then a exterior insulated roof to the wall here is using spray foam or some sort of, sealant or some sort of plug in there. And this generally works well, but we find more and more that it's really not it's not 100% foolproof. We see the biggest challenge we see is if you got, your spray foam plugging in there, if there's defects, those are obvious. But if the spray foam doesn't transition to the wood, doesn't transition to the membrane, if you don't have that transition material here, and you can see here where they stop the spray foam short, there's huge holes. And particularly below these joists here and below the joists here, there's, a lot of leakage is going to come through there. So it's not a guarantee, and you need the workmanship and the detailing there. And actually the best way to improve that detailing is just, do a little smoke test, do a little confirmation to show the builder that they need to get a bit more sealant in there. Exterior roof to exterior wall air barriers. This is coming up more and more, especially on larger multifamily projects. And so, you know, one of the first thoughts is, oh, it's just wrapped around the outside. And that can work. The challenge with this, especially in cold climates, is that, you know, the air barrier being out here, air can, in theory, get in here, and we see wet parapets and condensation occurring where this happens quite a bit. You know, you'll rip off a parapet of a 10, 20-year-old building, and it's all rotten in here. So we try to avoid this. We try to get the air barrier in the warmer location there. This also creates challenges, you know, mechanically attached parapets. You know, if these, you know, wrapping around here under pressure, they tend to billow, and when they billow, then you know, they open up joints, and you know, all these fish mouths and laps become more critical. So if you're going to do this, then it should be adhered on both sides. Another approach is the parapet plug. You know, so if you got exterior air barrier and transition to exterior wall, well, let's just plug it up with spray foam. In theory, that should work well, but in practice, what we find is that it's very challenging to get the spray foam into these small spaces. You know, extra framing, double framing, you end up with small gaps that don't really seal everything off. You can see here the gaps in the spray foam, just, you know, trying to get the gun in there. So, you know, applicator, you know, it can work. You just need to do a bit better job of the visual review and the confirmation to make sure that does work. And so what we do find works quite well, and a big lesson I think we've learned and transitioned to, is this notion of a pre-strip. So if you're going to have, you know, temper roof membrane on the roof deck, and you got a exterior wall air barrier, before the parapets go on, if they're platform framed, then you'll pre-strip some roofing membrane or a peel and stick underneath there, and that creates that very airtight transition. And a lot of the successful projects are incorporating that sort of detail. Lots of examples of this here. You can see the peel and stick going to the steel on the steel frame. You got flutes here that you're also trying to get around to and seal over, so that's going around. Blue skin there, membrane here. So, you know, that type of approach. And if you had to pick one detail to improve, this would be one that we recommend, where you're going exterior air barrier to flat roof. Other things we find that are challenging to seal. This is a very airtight project here that was, you know, quite a bit tighter than passive house. So the walls were quite good, the windows were good, everything was pretty good, except, you know, this looks decent, but when you actually test this, we found that almost in, you know, and what was happening is at the top, you know, so here was airtight along the bottom, but interestingly, a lot of air leakage occurred along the top of these, and you can see that every single location leaked. And, you know, a simple way to address that would have been to put some sealant in there, or some, you know, some forethought to pre-strip or put some sealant on top of as the sheathing went down. And that was done on the next project. So the builder learned from that to make it really airtight. There are things too, when you have double framing and you know, sealing those gaps, larger, smaller, very hard. And so if these are your remaining gaps, trying to seal those up at the end of the building is going to be hard.
Graham, on your infrared shot, a slide before, could you please explain how air leakage shows up on the infrared as heat?
Yeah, good question. Thank you. Yeah, so when we're using infrared, you're relying on a temperature difference between the indoors and outdoors. And so if it's colder outdoors versus indoors, and you'll see a temperature difference where it's hotter indoors, where infrared doesn't work that well is when the temperature is the same. We'll talk a bit about smoke and using other visual aids where infrared doesn't work. Yeah, thank you. So the next step, so we got our design, we've got some designs that, you know, and putting together that package and the drawings. The next step is build, okay? And when we talk about build, it's taking those details, those hopefully buildable details from your design phase, mock-ups, your construction sequencing, and then really putting together workable materials together and looking at, you know, implementation, let's say, of the design. So the first step in build is taking your details, looking at the sequencing, and wherever possible, looking at mock-ups. And mock-ups are increasingly becoming an important tool, either on the building as the first window or detail that you're doing of this, or maybe an off-site mock-up where you might test a whole bunch of different details on your project. this is an off-site mock-up for a window install and base of wall and roof to wall and brick transitions, and everything's going to come in here. A modular project here, being tested in the factory before it, repeated hundreds of times and working out the kinks and the details there. It's incredibly valuable to do the mock-up, but also then do the testing on the mock-up to help everyone see and visualize where leakage could occur. The other thing is, often the design will include a material selection, but then, weather and climate and time of year or even availability of materials will impact those choices. And so where we see challenges are, compatibility of materials with one material, one manufacturer to another. Adhesion is key, and adhering, peel and sticks or sealants when it's wet can be a challenge for some materials, and some it's not. Too hot, that impacts a lot of liquids. Too dry can also impact liquids. And so these challenges you really need to think about, and not having someone responsible and thinking about, okay, we got this material, this is going to be an air barrier, how are we going to sequence this in? Do we need to provide heat? Do we need to change the materials? All these things need to be thought about. The biggest thing, however, what we see, and we're seeing this more and more on our projects, is the notion of an air boss. And the idea with the air boss, this is a site super, someone on the GC team that is responsible for the air barrier continuity, the QA/QC, and the coordination with all the trades. So as soon as you have someone that cares or is accountable to air tightness, then things get a lot better. And so just caring and having that person there, be the pain in the ass to make sure that every detail and every detail is done properly, the joints are sealed up, all the trades are following, the rules, makes a huge difference. So the last step is confirm. Okay, and confirm includes a whole bunch of different activities that some people might call commissioning, and this is testing, commissioning, and just looking and visual review. Right, the first thing you can do: get up on the scaffold, go walk around the building, look at the air barrier, and most discontinuities are obvious. Tape's not sticking, or fish mouths in the tape, or poorly applied tape that needs to be sealed up. And if it looks bad, it probably is. If you can see a hole, it's likely that hole might actually go all the way back through into the building. And if you want to prove it to yourself, you can you can do a bit of testing, look into that, things like that, not sealing it up. So most of this is very easy to do. It just requires someone doing it. Infrared is an incredibly valuable tool because it allows you to see where air leakage is occurring. And so if you do testing when the building is positively or negatively pressurized, and being on either side of the building when that's occurring, potentially doing 2 scans, a positive and a negative scan to look at the difference, huge value in that, so you can see where air leakage is occurring. Especially from down here, you don't really know until you do a test that you realize you forgot to put a spray foam in here, for example, or the peel and stick wasn't properly lapped. So it allows you to scan a large area quickly, and then almost always you pair that with some sort of visual aid like smoke testing, and theatrical smoke or smoke pencils, or there's hunting smoke pencils and things you can get now. All these things can be used to help you see where the air leakage is occurring from afar, but also up close. And then you can use that as part of your QA/QC as well. The notion, when we look at, a lot of people talk about air tightness testing, you focus on this end result, this end test, where you take, fan doors, larger buildings, multiple fan doors, you set it up, pressurize, depressurize the building, and you measure the air leakage. It's useful, but it doesn't tell you necessarily where the leaks occur. It tells you if you pass or fail. And hopefully this isn't the only thing you're doing as part of your project. If this isn't the only thing you're doing, then you've missed an opportunity. Okay. And so when you look at quantitative testing, so a blower door or fan door test, you get a result. You get your building, you get the air leakage rate under negative pressure and positive pressure and an average. And you compare it to the target, and you're like, woohoo, we passed. And you get a picture of the fan door and people doing testing. It's interesting, but it's a lot of numbers, and it doesn't necessarily help you improve. Where possible, look at value add. And so you're testing a building, do an infrared scan. You're already there, you're already pressurizing, depressurizing the building, do infrared, do smoke, and do the extra testing to learn for that project or the next project. And that's the opportunity here. And what we're seeing is where people are doing this type of testing, we'll add this in, and you learn a lot more, especially the builders are learning a lot more from this rather than just the number. So I'm going to go through a few case studies here and some of the tightest buildings that we've looked at and what made them airtight. This is a unique project. It's currently our tightest US project in our database. There are other tighter buildings in North America, so it's no claim to be the tightest, but it is definitely one of the tightest around. It's a project in Spokane by Katera, designed by Michael Green Architecture. The project had a goal of net zero, and the building enclosure was designed with passive house principles for enclosure and airtightness. Okay, unique as it happens to be a mass timber structure. So mass timber, glue lams, cross laminated timber. There it is going up. The wall system is prefabricated, 2-story tall panels. The air barrier is a self-adhered vapor permeable air barrier system applied to the panels in the factory. It's got exterior insulation, cladding attachments. Those are packed up out of the factory and then brought onto site, and they're installed on site. So the panels themselves are quite airtight. Obviously, putting a membrane like that sandwiched and then over wood is going to be quite airtight, and then it comes into your details on site. So the windows themselves, just because of the large panels, were actually installed on site. And then the big thing you have is your joints. Okay, so between each of the panels, given the structural requirements of these panels and the movement of this building, actually had to be a flexible air barrier seal, so it's a silicone strip. And then the windows are installed into a rough opening and then caulked around the perimeter for air tightness. So this site applied air barrier requires a lot of workmanship. I mean, if everything else is done in the factory, but your site, you're applying sealant and then you're laying in a silicone strip. And so you're relying on workmanship. And so how do you make sure that workmanship is good if you're going for passive house or net zero target here? So there's more example here. So you can see it's quite challenging too. The sealant or the flexible sealant had to be sort of, to get the movement capability had to be, pushed in and in billows. Relying on a lot of sealant, it laps and everything else. So it's complicated, right? And so how do you make sure a complicated detail like this is going to be robust? Well, you do the confirmation, right? You got the builder on board with the details, and then you always do confirmation. So you do confirmation of a mock-up, you do field testing, we call it commissioning, you do air testing, water testing, usually at the same time, and then you have a QA/QC program where you look at these critical seals and you inspect and you test. And with the first time around, we had a fair amount of leakage, and we said, okay, now how do we fix this? And then so we implemented the QA/QC program with the GC, and then we did more and more testing. So if things aren't working, you do more testing to make sure and make it work. And here we're doing some smoke testing. So we're doing smoke testing on the inside. On the outside, the installer is actually there looking for the holes in the air barrier and sealing them up right as the smoke's coming up. Here's an example, a little bit of leakage. And here's a bad example, fail, right? And so you use that knowledge of the confirmation to seal it up. Had you just looked at this, you look at it and you're like, well, looks tight enough. Well, you need to get up close. You need to confirm. You need to prove it. And because of that diligent QA/QC program and the building itself, you can see it, you coming here to completion, cladding going on, terracotta. This building ended up at 0.034. And, code requirement would be way up here for Washington State at the time. Enhanced air tightness for Washington's here. The FIAS, the project requirement is 0.08, and this blew it away. And currently the tightest building in our US database. And that was really achieved by that design, good materials and details, the builder following up, the QA/QC, and the confirmation to ultimately led to this. Had you run the test without the QA/QC, I'm pretty sure it would have been somewhere up here. What are some other things we can glean from some other projects like that? In British Columbia, we're working on and have tested, and we're seeing across the industry, not just our projects, many large and tight passive house projects. And we're seeing a number of trends. Here are a couple projects, a church up in northern BC, 0.044. So, more than, 10 times tighter, quite a bit tighter, 0.42, the ACH 50. This project at mid-construction, 0.059, 0.44. And when we look at all these projects, what do they have in theme or are in common? The big one is they have a target that's quite tight. They have, almost in every single case, a rigid air barrier design, whether it be self-adhered membrane or a sealed sheathing or a sandwiched mechanical attached air barrier, something that's rigid, okay? Many of these buildings now are incorporating prefabrication. This had panels, the project had previously had panels. The builders in all the cases, there was someone that cared. They had an air boss or someone that actually, paid a lot of attention to this. In every case, there's lots of extra tape and sealing being done. In all the cases, there's a mid-construction test to confirm so they don't get to the end and realize that they failed. One of my favorite examples is a project just wrapping up right now. This project did not target passive house, but ended up twice as tight. And the reason it ended up there is ultimately design, build, confirm. The air barrier for this system is quite simple. Slab on grade, poly is a radon barrier, and transition details to the wall foundation. And then the exterior air barrier, self-adhered vapor, impermeable membrane up the walls. And then a lot of attention was paid at the roof wall interface here, pre-stripping parapets, spray foam where that wasn't going to work, mid-construction testing. And this building ultimately ended up, which is a school up in Whitehorse, 0.055 CFM per square foot. And the design target was 0.4. Absolutely blew it away and would have been tighter than a passive house if that wasn't what it's going for. And so we're seeing more and more of this where builder teams are actually blowing away targets that are not even, going for. And so a lot of success there, and, it ultimately falls back on that. So in summary, 3 key airtight buildings: design, build, confirm. Right? Design, we have many options. You have more than enough materials that you can use to achieve airtightness. The target is important so that you're up for you pay attention to the materials and details up front. Building is equally as important, and mock-ups and identifying the missing details and that air boss. The target is there to provide pressure to pay attention to your workmanship and perform that enhanced QA/QC. The target doesn't necessarily, it's just having that makes people pay attention. And then confirming, the visual review, simply visual reviews, and then testing, whether it be qualitative or quantitative. Why is target important? Well, it incentivizes you to do all these things before you get to the final test. So with that, we have time for discussion and questions.
Thank you, Graham. That was excellent. We appreciate it very much. So I'm going to give you a couple questions from the audience here. One we have that's interesting is the use and location of vapor open or vapor closed membranes in a northern climate.
Mm-hmm. Yeah, so if you want your wall membrane to be a vapor barrier or vapor retarder, then you'll use a vapor closed product. If you don't, then you use a vapor open one. And so the more, in a cold climate, the more exterior insulation you have, the less important that is permeable. But typically, with split, especially in wood frame, we'll use a vapor permeable membrane and insulation to allow some drying in that climate. But you can also design, like a lot of those projects you're seeing there are impermeable exterior membranes with a lot of all exterior insulation. So it really depends on your insulation and your design, your vapor control.
All right. Thank you very much. We did touch on, but I don't think we got into when you were doing the thermography, what sort of temperature differentials do you need to see in order for it to be effective?
Mm-hmm. Well, it depends how good your camera is, but usually, 5 Celsius, 10 Fahrenheit is what sort of a minimum you aim for. But surprisingly, building, especially on a roof to wall, the inside of those buildings, let's say in the summertime, will heat up a lot, and you can end up with like 30 degrees there, and it's only 20 degrees outside, Celsius, sorry, or 90 and 70 there, and so that temperature difference can often be enough. And so you may not plan to use infrared, but often it can be a useful tool in your back pocket. And more people have, the camera mounted infrared that are quite affordable now that anyone can do this.
That's great, Graham. I don't want to use too much of our audience's time, but perhaps one more question on testing. Mm-hmm. Could you comment a little on the testing standard that is, you often cited 0.4 CFM at mm-hmm. 75 pascals, but it seemed that was very easy, the way you showed it, mm-hmm. to beat. So mm-hmm. maybe you could comment on the derivation of those standards. And then the other part of that question on airtightness is, what about the mechanicals?
Yeah. So 0.4 is I would say, achievable target if you pay attention. And if you follow the, sort of design, build, confirm process, you're probably going to get, much better than that. And so it's a good starting point. And I think what Washington realized and US Army Corps very quickly, even BC is realizing, is that once you have that target, you sort of monitor the industry, see how they're doing, and then you can ratchet down from there. But it's a good starting point. I wouldn't start any higher. You could start lower. But that's, a decent starting point to shift the industry where people aren't building that airtight. And then mechanicals, yeah, obviously important. And so for the test, if you're measuring just the building enclosure, you're testing, with mechanicals generally sealed off. And the mechanical penetrations themselves, in service, the leakage is going to be higher, but there are supposed to be dampers and other components in there to really minimize that unintended air exfiltration or infiltration through your mechanicals as well. So when your building's operating, you're blowing air out or sucking air into those which are shut off for the test. So generally they're neutraled out. But backdraft dampers and bathroom fans and everything like that are important, and we're increasingly seeing that there is a need for better, more airtight dampers.
And in doing this, are you able to equate actual energy savings in terms of money to additional airtightness, or do you see airtightness and CI, or that is continuous insulation, as equally valuable? If you had an extra dime, which one would you work on?
Airtightness is usually your biggest bang for your buck. And you look at the things you put into really energy efficient buildings. I mean, insulation is very important, but the right amount of insulation, is all you need. But airtightness, you can't do harm in modern buildings with mechanical ventilation systems by being too tight. Okay, and that's so. All these buildings, mechanical systems are providing the ventilation, air, and so you want the building as tight as possible. And every ratcheting down of the tightness is going to result in energy savings and dollar savings. And we quite occasionally we'll take the original energy model with our design target, let's say 0.4, and we'll put the actual one in, and you can show the owner, hey, you're now saving an extra $500 or $10,000 per year by putting that in. Some of the, one of the case studies I showed, that air leakage was going to result in like $10,000 a month for a particular client. And had they, built it tighter, it would have, they'd be saving a whole bunch of that. So there definitely are financial incentives, and energy modeling can do a decent job of telling you what those savings could be.
Can a building be too tight? Is there a problem with it being too tight?
If you have a balanced mechanical system, it can't be too tight. People will complain about, obviously, balanced supply and exhaust on the ventilation side, so you're getting sufficient ventilation. That's obviously critical, but no.
That's great, Graham. I think we'll tie it up here as we're after 2.
Mm-hmm.
And if you'd like to give me the screen back. Thank you. If I can make this go, there we go. Perfect. First of all, Graham, thank you very much. That was a wonderful presentation, a great education on air tightness. If you want more information on air tightness, you can visit our website at dorken.com. We have some very specific information, as well as you can visit our Delta Academy site, where this webinar will also be posted, where we have other great information. Graham spoke a lot of self-adhering vapor permeable air barriers. In our case, this is Delta Vent SA. Dorken manufactures the base membrane Delta Vent SA in that plant I showed earlier, right in Germany. We're the only ones that actually manufacture the base product. It comes fully adhered. You don't need fasteners. It's also the only one with a self-adhesive front edge lap, so that you don't get that lap loosening problem that Graham showed on earlier slides. So you can achieve 50 perms, as well as that wonderful air tightness that Graham referred to repeatedly. In addition, we have Delta Dry, which is a great product for using behind highly absorptive claddings like stucco or manufactured stone. It adds drainage and drying energy and provides a lot of reserve for the durability of the building. It can go right in front of your Delta Vent SA vapor permeable air barrier. Here's a good example of a job in Lockhart, Texas, a bit of a rough climate. It used both Delta Vent SA as well as Delta Dry and Lath, which is Delta Dry with the lath pre-attached at the factory to save time when you're putting on your stone or your stucco. You can see a video on this on our website. Our next feature is a very impressive feature. It's coming up on the 31st of July. It features both Dr. Joe Stebrick and Dr. John Straub on the same show. These two have not appeared on the same stage since 2009, and we have them together to give their thoughts on the building enclosure, and you can hear them debate and argue Friday, July 31st, 1 p.m. Eastern Time. If you're still hungry for even more information, as I said, you can see Dr. Joe, you can see John Straub on our Delta Academy site. There's a whole bunch of learning lessons there, so take your time, peruse through there. And at this point, we thank you very much on behalf of Dorken Systems and RDH Building Science. We appreciate you showing up. Everyone on the who's attended will receive a link to be able to rewatch this on demand. Thank you so much for coming. Thank you very much, Graham.